Okay, so we're going to work on solving linear and quadratic systems, but this question is a little more in depth. It says for what value of b? So for our linear equation here, we know this is the linear because the x is the power of 1. They haven't given us a value of b. There's no y-intercept. They want to know for what value of b will this linear equation be tangent to this quadratic. So, because this is a negative, is it supposed to be negative 5? No, I think it's supposed to be positive 5. Sorry, I apologize. If we were to do a rough sketch here, essentially what we're looking to get is some parabola, and we're going to need a line that just touches. Okay, so the linear equation has to just touch only once this quadratic relationship. So we really got to start thinking of what we know about quadratics. Let's think about when we're factoring or using a quadratic formula. When is a quadratic only have one vertex? Do you know? Sorry, it always has one vertex. When is the vertex, or when does the parabola only cross the x-axis once?
When its vertex is on the x-axis.
Now, have you ever learned a formula or anything that deals with how to tell right away if that's going to be the case?
Like vertex form of a quadratic.
Okay, there is vertex form. Have you heard of the discriminant before?
Yes.
Yeah, okay. So the idea is the discriminant, right, so d is equal to, and the discriminant is part of the quadratic formula, right? We have our quadratic formula, negative b plus or minus the root. Okay. And the discriminant is the root part of our quadratic formula, right? This part here ends up being the discriminant. Now this is very important. Our discriminant being b squared minus 4ac. And what we discover is when d is greater than 0, we have two roots, right?
Yep.
That's not going to help for this because that means it's going to intersect twice. When d is less than 0, we have 0 roots, which is no good either because that means they won't touch. We're looking for the rare case when d is equal to 0. In other words, it has one root. And to have one root is to be tangent, to only touch it once, okay? So we talked about before with our quadratic linear systems that substitution will help us immensely, right? We can solve them by substitution. Problem being is we have an unknown in this question. Our unknown is being b. So we are going to use substitution, and then we're going to try to use the discriminant or the quadratic formula to deduce what our b value would be. So our two equations, our linear one was y was equal to 5x plus b, which is the unknown, and our quadratic was y equals 4x squared, is that right? Minus 15x plus 20? Yeah, I think that's right. Okay, so we can still use substitution. They're both already set equal to y, okay? So what we'll do is we'll take this y value here and plug it in for y in our second equation here. So we'll then equal to 5x plus b is equal to 4x squared minus 15x plus 20. Sorry, it's lagging a little bit here. Okay. In order to use quadratic formula, we need to set this equal to 0. So we're going to move the 5x and the b to the other side of the equation. So we're left with 0 is equal to 4x squared minus 15x minus 5x plus 20 minus, and I'm going to just highlight the b because this is going to be important for us. Simplify what we have. So 0 is equal to 4x squared minus 20x. And then we're left with our constant essentially being the value of 20 subtract b. Okay, so when we go to use the quadratic formula, we're in standard form, right? And here is our standard form. 4 is our a value, our b value is negative 20, and it just so happens our c value is an equation. Okay, so we have this equation here. We know that using our discriminant, d is equal to b squared minus 4ac, that we need the value of d to be what? Not sure? Okay, remember we talked about the discriminant. In order for this to work, it's lagging quite a bit.
0.
That's right. Oh no, don't go too fast. Okay, good. We need d to be 0 in this case. So what we're going to do with our discriminant formula, scroll down again, we're going to replace d with the value of 0, which means we'll be finding something that is tangent in this case. So we'll have 0 is equal to, and we're going to substitute our b value in, our b value being negative 20 squared minus 4 times our a value is 4, And in this case, our C value is a bit of an equation, 20 subtract B. So what we've now set up is a formula where we only have one variable. And now because we only have one variable, we can set equal to that variable and find an actual value for it. Okay? So we're going to go about solving this, and I'll do it in black from here on in. 0 is equal to, this should be 400. Subtract 16 times 20 minus B. Okay. Because we want to isolate, I'm going to move the 400 to the other side. Becomes negative 400 is equal to negative 16. I'm getting good at writing invisible here. Okay. We'll need to move the negative 16 to the other side by dividing both sides by negative 16. Okay. That'll leave us with 20 subtract B on the right side, and the left side, we'll bring up our calculator, 400 divided by 16 will give us a round. Yeah, it gives us a nice number, 25. Oh, this might work out good. What did I say? 25. Yeah. Positive 25. Great. So it's positive 25. We need to move 20 to the other side, which gives us 25 subtract 20 is equal to negative B, right? Which then means we get 5 is equal to negative B. We need the value of B being negative 5, which is actually what we guessed in the other question, right? So what we've now found is our linear equation, y is equal to 5x. We can replace our B value with what we found here, being negative 5. So B should be negative 5. And we're going to just quickly check. We have a little program here, and we've plugged this in already. So at 4, we knew we had two intercepts, one being at 2 and, oops, not what I wanted to do, the other being at 3. If we put the same equation, 5x minus 5, here it is, it gives us our intercept. It's tangent at this point. And now we would have to go about using our substitution to solve that point, but it looks like it's at 2.5 and 7.5 from our graph. They've helped us out quite a bit here in order to solve this. Okay? So let's look at our final answer here. Still a bit of work. We had to relate all of the knowledge we kind of had about quadratics to solve this.